Hi, I'm Carlos, and let me show you what I did to be able to solve the problem. Well, the first thing I did was to have the mass balance in order to have the differential equation set to be able to solve the problem and have that model to put it into Benzema and be able to simulate and then be able to simulate it. First, we have the initial differential equation, but on the left side of the equation, we have the volume. So in order to eliminate that term, we have to divide the whole equation by the volume. And when we do that, we have that the volumetric flow is divided by the volume, which is the ventilation rate, as it is indicated right here. The ventilation rate can be set at a constant number, which I will explain further into this video. So yeah, this was a differential equation that was obtained to model the concentration of CO2 in the classroom, and as a result we have these first order differential equations that can allow us to determine the difference of concentration throughout the whole time in the classroom. For the value of the variables, I did several things. First, let me show you the Excel I had. To calculate the volume, well, we headed into the classroom and take direct measurements of the dimensions of the classroom. And we measured the length, the height, and the profundity of the classroom. And when we do that, we obtain that the value for the volume of the classroom was 198.38 cubic meters. The R value was, I set it to 6, and the Q, which was the volumetric flow, I obtained it by solving this equation for Q, which gives us R times the volume. So like it is shown right here, I just multiplied the volume by the value of R, and I obtained the volumetric flow that gets in and out of the classroom is 1190.28 cubic meters per hour. So then I transformed that into cubic meters per minute. I just divided it by 60. The initial concentration was 420 parts per million, which you gave us. And finally, the rate of CO2. That's a little bit trickier, but it was interesting. The rate of CO2 was obtained using data from the study that you showed us in how cinema audiences change the composition of the air, where the average difference in CO2 concentration over an hour and 96 people present in the cinema room is 400 parts per million. So what I did, I just divided the 400 parts per million between the 96 people, and then I divided that value between the 60 minutes that an hour has, thus obtaining the rate of CO2 per person per hour. So this is the 400 parts per million between the 96 people present in the cinema room. So that gives us the parts per million per person per hour. And then I just divided the value that we obtained by 60, which is the 60 minutes that an hour has. And I obtained that the parts per million per person per minute is 0.0694. Yeah, so that's what I did. In order to translate the governing equation into the stock and flow diagram, this, which is the model in Benzema, I will show a little further into the video. But yeah, the things I took into account was that the concentration is a time-dependent variable. There are two mass inputs, which is in and S, which is the source, which is the breathing of the students, of the people present in the classroom. There's an output flow, which is going through the windows and door of the classroom as well. That the ventilation rate depends on the volume and the metric flow rate, and directly affects the input and output of the CO2. That's why it has these 2 arrows coming out of it and coming into in and into out. And finally, that the source is caused by the number of students present in the room and the rate of CO2, which I just showed you how I calculated. So then I turn this model into Benzene, which gives us this little thing right here, this little stock and flow diagram. So I obtained this graph, which shows that that the concentration does actually increase, but it does it very lightly, very poorly, you could say, so to speak, because the initial value of concentration was 420 parts per million, and by the end of the 2 hours, the model gives us that the concentration stabilizes at about 444.1 parts per million, which is a fairly optimal value, and that is due to the ventilation being very good, and that can be translated as the air quality is very good for people to carry out their activities. But the interesting part is the fourth question: how would these results change if we were to monitor the concentration of CO2 in our classroom for an entire day? Well, as we asked you, as we consulted you, we tried to put different values. I mean, we tried to model as the students vary from different time to time. This is because it's not the same number of students in 1 hour or in one class, and we definitely don't have students or people even coming in or out of the classroom by night. But we didn't make it function in Benzene. But a Benzene can be, what I did to simulate different conditions of students was just to run different simulations like this. Let me get this out of the way to be able to show you. What I did was to change the number of students, because in the first simulation that is shown right here, the blue line, we have a number of people of 35 students. Then we have 40, which is pretty similar. Then we have 6 or 8, I don't remember well, which gives us a pretty straight line. I mean, the concentration doesn't change very much. And finally, with 20 people, which is the value between 6 and 35, which gives us this blue line right here that is set between the two other lines in concentrations. So let me show you a little bit of what I did. I basically changed the number of students. For example, we have 20 right here, so let's put it to 60, just to put an example. And let's run simulation 8. Let's run it. Let's check the graph. So yeah, the simulation 8 right here, the number of people is this. The concentration, we can see that is increasing very rapidly. So this shows that the number of people that is present in the classroom does affect the concentration in different ways. And yeah, so that's it. I hope that you like this video. I actually was very excited and very interested in solving the problem and making it more real, for so to speak. But I liked it, and I hope we can see more of this in the future.